Good morning, everyone. We are the Group 3.
And before we begin our report for today, we will introduce ourselves first. I am Maureen Joy A. Ilana,
Maya Pichain, Elsa Magam,
Andrea Gail D. Valencia,
Sharon Hilmir, Raylene P. Morales. For today is about Biot-Savart law and Ampere's law. So these are the subtopics of our lesson. So Biot-Savart law statement and derivation, Ampere's law statement and application and limitations. So what is Biot-Savart law? The Biot-Savart law is an equation describing the magnetic field generated by a constant electric current. It relates the magnetic field to the magnitude, direction, length, and proximity of the electric current. Biot-Savart law is consistent with both Ampere's circuit law and Gauss theorem. The Biot-Savart law is fundamental to magnetostatics, playing a role similar to that Coulomb's law in electrostatics. Biot-Savart law was created by two French physicists, Jean-Baptiste Biot and Félix Savart. They derived the mathematical expression for magnetic flux density at a point due to a nearby current carrying conductor in 1820. Viewing the deflection of a magnetic compass needle, these two scientists concluded that any current element projects a magnetic field into the space around it. This is Jean-Baptiste Biot and Félix Savart. They are the two French physicists who came up with the Biot-Savart law. So, Biot-Savart law is a fundamental principle in physics that explains how current carrying wire produces a magnetic field. It states that the magnetic field produced at any point in space by a current carrying wire is directly proportional to the current flowing through the wire and the length of wire segment, and inversely proportional to the distance between the wire and the point where the magnetic field is being measured. In simpler terms, the Biot-Savart law tells us that if you have an electric current flowing through a wire, there will be a magnetic field through around that wire. The trend on how much current is flowing through the wire, how long the wire is, and how far away you are from the wire. This law is incredibly important in the study of electromagnetism, as it helps us understand the behavior of magnetic fields around current carrying wires and the interaction between magnetic fields and the charged particles.
So this is the law, the Biot-Savart law statement and derivation. The law can be stated as hence dB is proportional to I times dl times sine theta over r squared, or dB equals k I times dl times sine theta over r squared. So, para masubstitute na ayo, ang the dl is the infinitesimal length of conductor carrying electric current, which is this one. Ang I, it is the unit vector to specify the direction of the vector distance or from the current to the field point. So, para siya masabtan, this is the...
Now we look at the Biot-Savart law. Now, Biot and Savart were two scientists who were looking at the source of the magnetic field. And experiments showed that electric currents can create magnetic fields. But it depended on a few things. It depended on how much current you had, depended on how far away you were from that current, and it also depended on other geometry factors. Now, the Biot-Savart equation is kind of complicated, so let's take a few minutes here to sort of break this down. First off, we have the current I. We know that the magnetic field from a current has to depend on how much current we have, so that's our I in the equation. All of this stuff over here with the integral, well, that describes our geometry and our distance. And this little guy over here is our magnetic constant. Let's look at that a little bit more closely. So this magnetic constant, well, it's given this symbol here, and that's actually the Greek letter mu with a subscript of 0, so that's a mu naught. And its name is the permeability of free space. As a value, this is a constant 4 pi times 10 to the minus 7th Tesla meter per amp. You could also multiply that 4 pi out, and you could write mu naught as 1.257 e to the minus 6 Tesla meter per amp. Now you remember we had an epsilon naught back from electrostatics, which was the permittivity of free space. And epsilon naught and mu naught together are related to the speed of light. So now back to our equation, and let's focus in now on the side where we're talking about geometry and distance. To help explain this a little bit clearer, let's actually give ourselves a diagram. So imagine you've got some wire. It can be curvy, it could be straight, whatever, out in space. And we want to find the magnetic field at some other point in space separated from that wire. Well, the ds part of our integral over here stands for a line segment. And we're going to have little line segments all up and down this wire. And notice that each one of these little line segments is the same length, but they could point in different directions. Now the r here on the bottom represents the distance, and it's specifically the distance from a line segment to the point P in space. And again, each different little line segment may have a different distance from that segment to our point in space. The r hat part here is a radial direction, and the hat lets us know that it's a unit vector. So it points in the same direction as this radial distance, but it's only indicating the direction. It doesn't go all the way there. And again, each point along our line may have a different r hat radial direction being shown. Now the top part of this integral here is a cross product, and it's the cross product between these two vectors for the line segment and the radial distance. So when you take that cross product, that also helps determine the direction of the magnetic field. We can do that for each individual segment, but the integral tells us that what we really want to do is we want to sum up the contributions over all of those different line segments. And that will give us the overall magnetic field at our point P out in space. So while the equation itself is a little bit complicated, it helps to break it down into things that we can understand from a picture of geometry. Now let's take a look at the equation from the standpoint of units. Well, we said our mu naught had a constants of Tesla meter per amp. Current, we know, has units of amps. 4 pi doesn't have any units. The ds part of our integral has units of meters, while the r squared part has meters squared. And my r hat, you might think it's meters, but it's a unit vector, so again, no units there. So once we've collected all these together, what we see is that we have an amp on the bottom and the top of the equation, which are going to cancel each other out. And then I've got 2 meters on the top and a meter squared on the bottom, which will also cancel each other out. So everything from my right-hand side, all I've got left is Tesla, which is the unit I expect for the magnetic field. So every time we've got a current-carrying wire, we're going to end up having something of this form, which ends up having a units of Tesla. So that's the end of our introduction to the Biot-Savart law.
So for now, let's move on to Ampere's law. Ampere's law is a useful law that relates the net magnetic field along a closed loop to the electric field current passing through the loop. It is first discovered by André Marie Ampere in 1826. André Ampere formulated the law based on Ørsted's as well as his own experimental studies. This law can be regarded as an alternative expression of Biot-Savart law, which also relates the magnetic field and current produced. But it is needed an exclusive calculation of the curl of B, and that calculation leads to the limitation of the usual form of this law, its validity holding only for steady currents. After 4 decades later, James Clerk Maxwell realized that the equation provided by the Ampere was incomplete and extended his law by including the magnetic field arises due to the electric current by giving a mathematical formulation. So, Ampere's law is a fundamental principle in electromagnetism that describes how electric currents produce the magnetic fields. And the law states that the magnetic fields created by current carrying wire is proportional to the amount of current flowing through the wire. So, in simple words, Ampere's law tells us that if we have a wire carrying an electric field current or an electric current, it will create a magnetic field around it. The strength of the magnetic field depends on the amount of current flowing through the wire. This law is important in understanding the behavior of many electrical devices, including motor, generators, or transformer as well.
So, important notes. All currents have to be steady and do not change with time. So, when we say steady current, it is also known as the direct current or DC, and it is a type of electric current that flows in a single direction with a constant magnitude and does not change time. This means that the current remains the same over time and does not oscillate or fluctuate in the value. So, the second one is only currents crossing the area inside the path are taken into account. When we talk about currents crossing the area inside the path, we are referring to the concept of electric flux. What is electric flux? When we say electric flux, it is a measure of the electric field passing through a particular area, and it depends on the strength of the field and the size of the orientation in the area as well. So, in simple words, the statement of only currents crossing the area inside the path are taken into account. It means that when we calculate the electric flux through the particular area, we are only considered the electric field lines that pass through the area. So the third one is current have to be taken with their algebraic sign by using the right-hand rule. When we say the right-hand rule, it is a technique used in physics to determine the direction of a magnetic field or the direction of the force acting on a charge in a particular magnetic field. When it comes to taking currents with the algebraic sign, the right-hand rule is used to determine the direction of the current flow. By convention, a current flowing in the direction of the fingers, as Marian will demonstrate what is the right-hand rule. Yes.
This is your represents the wire or the conductor that you're using, and the thumb is your call this one?
This one is the represents the I or the current one.
And this represents the magnetic field. Your fingers wrapped around the pen represents the magnetic field surrounding the wire. That's the right hand rule. Always remember so that
Therefore, when we calculating the effects of electric currents, it is important or it is necessary to take into account the algebraic signs and direction. And this can have a significant impact on the behavior of the system. The right hand rule, this one, is a useful tool for determining the direction of the currents and the magnetic fields and can help ensure that the current algebraic sign is assigned to the current that is being analyzed.
Next, we have applications. Magnetic field inside a long cylindrical conductor. So before that, magnetic field, as we know, is a region in space where a magnetic force is experienced by a magnetic object or a moving electric charge. Magnetic fields are generated by moving charges such as those found in the electric currents, and they can also be produced by magnetic materials such as magnets. And magnetic field inside a long cylindrical conductor. A long cylindrical conductor is a type of electrical conductor that has a cylindrical shape, cylinder shape, and is typically much longer than its diameter. It is often used in power transmission and distribution systems, as well as in electric motors and generators. So, a cylindrical conductor with radius carries a current. The current is uniformly distributed over the cross-sectional area of the conductor. Find the magnetic field as a function of the distance from the conductor axis for points both sides and outside the conductor.
We applied it in order to find the magnetic field produced by a long cylindrical conductor. Alright, if you have inside here we have a closed loop integral of B dot dl. So let's first look at this. So we really want to try to simplify this expression as much as we can. In order to simplify it, help the magnetic. Also, action. This depends on how to a long a loop that is just a little bit of length that goes out higher, right? So it is a short. Any little vector dl. Vector constantly move around my loop. Okay, now let's consider the direction of magnetic field B produced by a current that's going upward. For this, what you want to do is you want to use the right-hand rule. And the right-hand rule is pretty straightforward. There's a cartoon over here depicting it. And here I have a cylindrical conductor, right? And imagine I have a current going up in this direction. Right here, if I place my thumb in the direction of this current, so place my thumb going, my fingers give me the direction of the magnetic field. And you can see that my fingers are simply going to curl around circumferentially around this like cylindrical conductor. So if I now think about this, I think anywhere on the loop that I drew, the direction of the magnet produced by this current. So let me go ahead and plot it. Here the magnetic field would be like this. And after that loop, just go around again, change direction everywhere. E something here. I have vector people, and you see they are parallel to each other. Simply going around that loop, and that is important because this scale dealing with a circular loop, all it's going to be so they're paired each other. The integral here of is going to be constant. Right? Direction changes that's producing the magnetic field. So this is B, and now if I add up all of the little dl contributions, again, just adding their magnitude, what you end up getting is 2 pi multiplied by the radius. In this case, it's a little r. So for cylindrical wires, whether they are one-dimensional or have some finite size, is always going to be the same. Okay, so B multiplied by 2. Now let's go look at the other side. Everywhere. Right, so that means that my radius is bigger than the radius of the wire. The radius of the wire is big R here, as I'm bigger. If I take a top-down view over here, this is what it looks like. Okay, so I have the wire here in blue, and the current is coming out of the page. Now, sometimes they define the current density. In this case here, I'm taking the current density to be a constant value. This is simply the total current divided by the area in which the current is traveling through. So again, if I'm thinking about a circle over here, in this case, it's simply the current divided by the area would be pi and big R squared. Okay, so this would be kind of a current density in case that is provided to you. So what else? Well, we want to look at it from the top-down view. Let's go ahead now, and if you consider our right-hand rule again, if I plot the vectors, I should have my vector B, which is going around, right? Doesn't matter where you draw it. It should be tangent to the Amperian loop here. It's simply going around the circle. Let me just draw a couple more. This is what B looks like. And since it's always the same distance away from the source, the magnitude of B is the same everywhere. Just the direction is changing. Again, we had our vectors BL, and we said that the left-hand side appears long. Set. So the integral pi by 2 pi you have to be a little bit careful here. Which R would you use? Little r that goes in here for my total circumference, the wire in this case. So a little bit careful. That multiplied by mu 0. And what's the other term? The other is how much current through it, right? Again, it's all of the current that through the wire. Okay? All of simply the current I. That's it. If you really wanted to, you could do it in terms of the current multiplied by the total area of the wire. Be multiplied by pi squared. You see at the end of pi r squared. You cancel that apply. But that's it. Other one, well, you have B over here on the left-hand side. You simply bring all the other terms down. What you have, mu 0, 2 pi divided by. This is our equation. The field magnitude is by the wire. What is this equation applicable? Whenever radius inside the wire.
So from Ampere's law, we have the line integral B dot ds is equal to mu sub 0 times I. We will take the Ampere loop to be a circle. Hence, for points inside the conductor, The Ampere loop, this is the Ampere loop, this one will be a circle with radius r, where r is less than the big R. The current enclosed will be I over pi r squared times pi small r squared. So we have this formula. Yes, this formula. And then for points outside the conductor, the Ampere loop will be a circle of radius small r, where small r is greater than r. The current enclosed will just be I. So this formula, we will see more detailed explanation for this formula in the video that will be shown in the next slide. Next, we have magnetic field of a solenoid. Before we move on to reading this, a solenoid is a coil of wire which is designed to generate a strong magnetic field within the coil. Wrapping the same wire many times around the cylinder creates a strong magnetic field when an electric current is passing through it. Here, in the image. This is the wire, and then you wrap around many times like that. So, a solenoid consists of a helical winding of wire on a cylinder, usually circular in cross-section. If the solenoid is long in comparison with its cross-sectional diameter, and the coils are tightly wound, the internal field near the midpoint of the solenoid's length is very nearly uniform over the cross-section and parallel to the axis, and the external field near the midpoint is very small. We will use Ampere's law to find the field at or near the center of such a long solenoid. The solenoid has n turns of wire per unit length and carries a current. So here is the Ampere's law. And then following the integration path, we have the Ampere's law. Wait, from what I've understood in the so following the integration path, so we have the line integral a to b, then we have c to b, c to b, and then we have b to c, d to c, then last is a to b, a to d. Then we just copy this one for four copies, and then because here it's stated that the solenoid's length is very nearly uniform over the basta. To further explain this, we have a video in the next slide.
Video, we saw that if you have an electric current carrying a loop, then it generates a magnetic field that's very similar to that of a bar magnet. But it doesn't quite resemble a bar magnet, because if you look inside the bar magnet over here, then you can see that there is this long region where the magnetic field is pretty straight. Straight and parallel to that. Then notice that field lines are straight is very. And so this is a big argument. So now the question is, how do we create something that generates a magnetic field perfectly like a large bar magnet, where we have a large region where the magnetic field lines are pretty straight inside? That's what we should find out now. So how do we do this? Well, what if we bring in another current carrying coil over here? So let's say we bring in another current carrying coil and place it down here somewhere. Then it's identical to this one, so it's going to produce an identical magnetic field of its own. And I'm going to show that in a different color over here. But remember, magnetic fields can never ever intersect. And so, the total magnetic field of these two coils together won't look like this. Because here they are intersection. So you know what's going to happen? The two magnetic fields are going to merge together and give us a new magnetic field. It's going to look somewhat like this. Ooh, look at the combined magnetic field. We now have a straight.
Last, we have limitations. The limitation of Ampere's law is that it is valid only for steady current. As mentioned in the video, the magnetic, the magnetic is only for one direction like that. It doesn't go up it doesn't bend like that. The conventional form of Ampere's circuital law was pointed out by Maxwell. He introduced the concept of displacement currents. It's the current associated with time-varying electric fields. To generalize Ampere's circuital law, even for non-steady currents, it was this generalization of Ampere's circuital law that played a crucial and central role in the development of Maxwell's electromagnetic theory of light. And for additional knowledge on the limitations, we have it's stated here, it's the validity. So in that, Ampere's law is only valid in situations where there is a steady current or steady electric field. It's stated here. It does not apply to situations where the current or electric field is changing with time. Another is we have the symmetry. Ampere's law is based on the assumption of symmetry. It assumes that the current is distributed uniformly throughout the cross-section of the loop, and that the magnetic field is also symmetric around the loop. In situations where the current is not distributed uniformly, or where the magnetic field is not symmetric, Ampere's law may not apply. So it's just an assumption that it is distributed uniformly. Next is we have closed loops. Ampere's law only applies to closed loops. It cannot be used to determine the magnetic field for an open-ended wire or a wire that terminates in a resistor. Next is we have the magnetic materials. Ampere's law assumes that the magnetic field is solely due to the current flowing through the loop. It does not account for the effect of magnetic materials, which can change the magnetic field around the loop. Last is we have the relativity. Ampere's law is based on classical physics, which does not take into account the effects of relativity. In situations where the current is very large or the magnetic field is very strong, relativistic effects may become significant and Ampere's law may no longer apply. So that's all for our report. Thank you.